Hey everybody. So this is our last chapter before the exam. Um, chapter 6, what we're going to do is basically what we did in chapter 5, but we're going to add friction. And then there's 3 quick topics at the end that won't be on the exam, but I'm going to talk about them because they're in chapter 6. And now that we're kind of doing Newtonian forces, we can actually analyze some of the stuff we couldn't do before because we didn't have the mathematical tools, which is fine. I'm going to start this off by talking about kind of what we just did in chapter 5 again. I realized that I left off a really important problem. So I want to review what we did, and then I want to go over a really important problem, and then we'll get into friction. So remember that the whole point of chapter 5 was using Newton's laws to figure out the acceleration of a system of blocks. It could be 1 block, it could be 2 blocks. In this first problem, what I want to do is I want to do the case where we have a block on an incline connected over a massless pulley. We do that just so that we can change direction to another block that's on a flat surface. This will be 45 degrees. I'm going to tell you that it's going to try and slide straight down, which means, sorry, this is M2, this is M1, which means this one's going to head to the left. So first thing we do is we draw a free body diagram. Recall that for M1, okay, we have some theta, and M1 has a weight vector that goes down, which is equal to mg, M1g I should say, and it has therefore a weight in the x if you get rid of this, and it has a weight in the y, and that is M1g sine theta, and this is M1g cos theta. It also has to have a normal force, and we're going to put, this will be our positive acceleration direction, this will be our positive y, so this will be our positive x, okay? It also has to have a tension because it's connected by the rope to M2. For M2, we're going to say y is positive up and x is positive that way, and we'll do the free body diagram for it in a second. So all we have to do is draw the forces. We should actually write x and y. Mg sine, M1g sine theta, and tension, and M1g cos theta. And our acceleration for this guy, acceleration 1, goes that way. For number 2, we have the normal 2 and the weight 2, which is M2g, and it has a tension because it's attached to this rope to mass 1. I'm going to let y and x be the same. So y and x, and A2 is also going to point in that direction. Now remember why we do this. We do this so that we can write Newton's equations for the motion. It's a visual representation. And so what we write is M1 AX and M1 AY. All right, 1 there. M2 AX2 and M2 AY. This means the acceleration in the x direction of block number 1, right? So I know that these are 0. So this is N2. M2 goes up, weight 2 goes down. And this is also 0. N2 goes up, and I'm sorry, weight 1 goes up. And remember the component in the y of the weight of M1 is M1g cosine. This is M2g. So now we need to do A and X. What these give us is that N1 is M1G cos theta, and N2 is M2G if we need it. You'll see later in this lecture when we need it and why we need it. So M1AX, remember A is positive that way. So we get M1G sine theta minus T. And M2AX is simply T. So we can see right away that we can substitute this T into here, and what we get is well, before we do that, since they're massless and frictionless ropes, A1 in the X direction and A2 in the X direction have to be equal. However this mass moves, this guy's gonna move the same. If he slides down 5 meters, he slides to the left 5 meters. So we're just gonna call this A. And what we get is M1A is M1G sine theta minus T, but T is M2A, or M1 plus M2 times A is M1G sine theta, okay? And we can plug in whatever we want. What's important here is that if we look at this, what we got was that A was M1G sine theta over M1 plus M2. If we go back and look, if we move this over, that's what we get. And what we see here is if M1 were 0, we would get 0. So if there were no mass 1, mass 2 would just sit on the flat surface. If M2 were 0, we would get M1 over M1, we'd get G sine theta. So A is 0. If M2 is 0, then A is G sine theta, which was what we found for the acceleration of mass 1 down an inclined plane with no other forces and no friction on the plane. Okay, that's all we have to do. We could put some numbers in. If M1 and M2 were, let's say, 4 kilograms, and the angle were 45, we could find what A is. So let's do that. If these are both 4, what we get is we get 4 over 8 times 9.81 times sine of 45 degrees, and that equals 1/2 times 9.81 times root 2 over a half. So 0.5 times 9.81 times sine of 45 is 3.7, 0.47 meters per second squared. Now I can ask you on an exam, okay, well, if this thing slides from rest 3 meters, how far does this one go? 3 meters. But what is the final velocity of both of them? The final velocity has to be the same because they're attached by stretchless, massless, frictionless ropes. It's important. We have V final, V initial is 2A, X final minus X initial. And if I told you starts at rest and slides 3 meters down incline. I should also note that this A, it's the same for both of them, but it's A down the incline and A to the left. Plugging this in, rest means this is 0. We always can assume that is 0. So we get that V final is 2A X final, or 2 times 3.47 times 3 meters. And that gives me square root of 2 times 3 times 3.47 is 4.563. 4.563 meters per second. I could ask, how long does it take to slide? Again, we have V final is V initial plus AT. V initial was 0. So the time is simply V final over A. This V final I just found divided by the A I found is 3.47, is 1.3 seconds. Okay, 1.31 seconds. So I'll just call it 1.3 seconds. And that's everything you would need to do on an exam for this problem. You would start off by drawing your free body diagrams, give me the equations, solve the equations for A, get A as a number, And then use A in some kind of constant acceleration problem. That's it. It can get a little more complicated when we have more objects and more forces. It can be more complicated because what if I gave you A, or I told you that A was 0 because of constant velocity? We'll talk about that. So if you have some of the variables, you can solve for the other ones in the A equation, right? You're not necessarily always solving for A, but in this case we did. So moving on to another problem. I like this problem a lot. This is probably one of my favorite physics problems because it's easy, but you have to know what you're doing to understand it. So what you have is you have a pulley, massless. It's just redirecting the shape. And you have two masses attached by a rope over that pulley. So if mass 1 falls, mass 2 rises, and if mass 2 falls, mass 1 rises. Okay? And so we're going to say that mass 1 is 3 kilograms, and mass 2 is 8 kilograms. And by your own physical intuition, whichever one's heavier, that's the one that's going to fall, right? So we know that this thing's going to fall that way, and this one's going to rise. When we do the free body diagrams on 1 and 2, we have to do the tension. There's no normal force because they're hanging. There's a weight. This will be weight 1, which is m1g. And we need to draw, we're going to say that y is positive up and our acceleration is positive up. If that's positive up, the acceleration needs to be positive down for 2. The accelerations will be the same because they're tied to ropes. This is also tension, and this is weight 2, which is m2g. Okay? And now, all that's left. Oh, and I should note that I'm going to say that y is positive up on this side as well. Although it really doesn't matter because this, we're going to use A, and I want to show you that. So really, I don't need to tell you that y is positive up. It's helpful, but it really depends on A. So if we write m1A, we don't need to do x. There's no x motion here. If it's positive up, then t is positive, and m1g is negative. For this one, since it's down, m2a, the weight 2 is positive, and the tension is negative. So notice the difference in these two equations. This guy's positive because the acceleration is going down because it's falling. Okay, this force, this weight is in the positive direction. The tension is in the negative. In this one, since it's being pulled up, the tension is in the positive direction and the weight's in the negative direction. Okay? Now all that's left is solve this for t, and I get m2g minus m2a. Add tension to both sides, subtract m2a from both sides. That gives me m1a is m2g minus m2a minus m1g. Let's move this over and combine like terms. Is m2g minus m1g, or better yet, A is m2 minus m1 over m1 plus m2 times g. Okay? Had you not been consistent with your acceleration, this might end up inconsistent. So be consistent. Make A go positive around the rope, along the rope, I should say. And notice something. If I remove m2, if m2 is gone, I get negative m1 over m1, which gives me negative g as the acceleration, which tells me if there's no m2, m1 falls. If I get rid of m1, I get a is g, which means that 2 falls with an acceleration in the downward, in the g, or in the downward direction, an acceleration of g. And it's positive because we're assuming that we're going in the negative direction or the down direction, right? That's an Atwood machine. It's even simpler than, it's almost, I think, simpler than doing even a flat surface, because you don't have to worry about normal forces. You just have to worry about the tensions, Later on, when we start worrying about whether or not a pulley can rotate, we're going to need to worry about the rotation of the pulley. The other reason why I really like it is if we look at it, we can see that this is the net force. This is the total mass times the net acceleration on the system is equal to the two forces. The two forces on the system, if you just drew this as one system, there's a weight pulling down due to M2G, and there's another weight trying to pull it in the other way, M1G, and it's trying to make this thing rotate almost, right? So you have these two opposing forces that are trying to make this thing rotate either clockwise or counterclockwise. That's pretty cool. It's easy to see. Atwood machines are really important because they actually transfer gravitational energy into other types of energy, but you don't need to know that yet. All you need to know is how to do this. And because we didn't have a problem where we had two masses on a pulley connected together, I wanted to do it for you. That's it for the review. We're going to do a bunch of friction problems in a little bit, but and you're going to see we're going to do a bunch of this stuff all over again. But yeah, I just wanted to make sure you guys know what we're doing and what we're trying to do. Okay, so, and I spelled friction. So when I don't know why this does this, but fine. Friction is F-R-I-C-T-I-O-N. So we need to talk about what is friction. And so far, we actually assumed that friction didn't exist, that we are on frictionless surfaces. If you take your hand, I'm assuming you're sitting down, you take your hand and you put it on your desk in front of you, or even on your pant leg, maybe not your pant leg, but something that's rough, and you try to push your hand, you feel how the surface kind of stops you, it kind of grips you and slows your hand down. We all know what friction is, but we may not know what it actually is. It's common to think of it, even our book talks about it, as like there's this rough surface and the rough surface of your hand, and they're, you know, interlocking and grating against each other. But it's more than that. It's also electromagnetic forces between them repelling each other. It's weird. It can be if there's some fluid, it can be properties of the fluid, it can be a lot of different stuff. So we hide it all. We hide it all by saying that the force of friction is negative mu n, where n is the normal force. So if an object, like a block or your hand or whatever, we're on a surface with friction, it's got a normal force and it's got a weight, right? But it's got this force of friction, and that force of friction depends on how hard or how much of the weight is pushing into the surface, how much of the weight of the object. This is mu, it's a Greek letter. It's just a coefficient. And we're going to talk about this when we talk about drag. But what that really tells you is that we're hiding the physics. We measure what the friction is, and whatever we find, we assume that it's equal to some constant mu times the normal force. And we try to figure out what that coefficient is experimentally, doing experiments and measuring things. But we don't really understand the physics or even acknowledge the physics that are hidden behind mu. So those intermolecular forces, or all sorts of things, you know, because friction could be air resistance too. You could have density that affects it. You could have all sorts of weird things that affect it. We're going to hide all of that. The second important thing is this negative side. If I pull this block this way with some force, or actually I should say with velocity, so this block tries to move, the friction force is always opposite the motion, okay? And I should draw this. This is not a vector on the free body diagram, but this would be. So whatever direction is moving, if there's friction on the surface, the friction force is in the opposite direction. So we don't really need to put this negative sign. In fact, I urge you to not put it, to use your free body diagram to understand where the friction vector is and what the sign on it is. But that also means that when we do problems, we really need to consider which way the object's moving if there's friction, and make sure that our friction vector points opposite of the direction that it's traveling. When we do energy, friction is going to come up again in its own special case, because friction actually takes work out, it takes energy out of the system. But in the Newtonian formulation, it's just another force. It has a magnitude of mu n. There's actually two different types of friction that we're going to talk about next. But and we just do everything we've done so far for chapter 5. If there's friction, we just add another force. There's a few little considerations we have to make for that friction force that aren't so straightforward. It's not as easy as just slap another force in the free body diagram, but in some ways it is. So there's actually two types of friction, and don't do this, you might hurt yourself. But if you take your hand and put it on a rough surface and slowly push harder and harder and harder, eventually your foot slips. But before it slips, nothing happens until you apply enough force for your hand to basically break loose of the friction. Before it starts moving, that force that's pushing back on your hand is called static friction. When you're standing and pushing like on a wall but not going anywhere, that's static friction. If you were standing on the side of the hill, what keeps you from sliding down the hill is static friction if you're not moving. A second type of friction is kinetic friction. Your car tires actually have kinetic friction acting on them as they roll. When you walk, it's the kinetic friction that well, some of it's static, but kinetic friction is friction due to motion. If you're moving, you have friction. And kinetic friction is what we 99% of the time in the class will deal with. Static friction is a special case that we talk about now, and in certain cases we say, yeah, there's friction in equilibrium problems in chapter 12. We say, yeah, there's static friction there. But for the most part, we don't even talk about it again. However, static friction is written as minus mu s n, and kinetic friction is usually written minus mu k n. When I write mu n, I sometimes mean one or the other. It's really, I leave these off all the time. Sometimes I'll write them wrong. Really, friction is just mu n. There's a coefficient. That coefficient is usually 0.001 to 1. It can be bigger, but the static friction, though, is always bigger than the kinetic friction. So basically, if I'm pushing on something, imagine you're pushing your friend's car. It's stalled, it has a flat tire, you're pushing it. You push and push and push until it starts rolling. And once it starts rolling, what happens? It gets easier to push. If you start pushing something across the table, it might take a second to get it moving, but once it's moving, it's easy to maintain the motion, because kinetic friction, the coefficient of kinetic friction, is always less than or equal to static friction. That has to be true, because if the kinetic friction was greater than the static, it would never move, right? In a weird way, right? I don't know if that makes sense. Basically, if you had to overcome the static and then you still had greater friction than that, yeah, I'm sorry, that would totally be true. It would never work. So mu s is always greater. What happens is you start pushing with a force, right? And it gets bigger and bigger and bigger and bigger and bigger. And then it suddenly breaks loose and it goes. And so this regime is your static friction regime. In fact, it actually kind of does this weird little dip. And then this is the kinetic friction. And so this is the force required to push. It doesn't actually start moving until it hits right here, where you where you overcome the complete static friction. We'll talk about that. And then once you do that, you're in kinetic friction. Most of the time in the class, we're going to talk about objects moving and they're on a surface with friction. And so you have to account for the friction, and it's kinetic friction. It'll make more sense as we go. The friction vector, as I said, if I'm trying to slide down an inclined plane with friction, the friction vector always, so this is my velocity, always points opposite the motion. So whichever way the object's going, friction points in the opposite direction. When I look at this, if I draw a free body diagram of this, I have N, I have weight in the Y, I have weight in the X, and I have friction pointing opposite. And this thing's supposedly accelerating downward. If it's sliding down, it's accelerating. Maybe acceleration is 0, but it's sliding down the incline. The friction tries to stop the motion, always. Okay, so now let's talk about this. So let's say we have a surface with static friction, a coefficient of static friction of, I don't know, 0.7. Coefficients of friction have no units, they're just a number. So I have this block sitting on a flat surface, and this block weighs 2 kilograms. It's sitting on a flat surface, and I try to push it with a force. My free body diagram, it has a normal force. It has a weight, which is M1G, where M1 is 2 kilograms. And then, because I'm trying to push with the force of static friction repels that force. It works opposite the force. So the static friction basically is going to work mostly against the net force. We'll see something in a minute where we don't really know, which is why we don't really worry too much about static friction. But drawing this, okay, this all happens before the object can move, which means there's no A, right? There is no Y is positive up, X is positive to the right. There is no acceleration in this. So MA in the X and MA in the Y are both 0. MA in the X is whatever my force of push minus the force of static friction. I'll come back to that. This is N minus M1G. So my normal force is M1G. And my force is equal to the force of static friction. Static friction is mu N, which is mu M1G. And as I said above, that's 0.7 times 2 times 9.81. So 0.7 times 2 times 9.81 is 13.7 newtons, 734 newtons, okay? That is the force of static friction. Forget this for a minute. The force of static friction has a magnitude of 13.734 newtons. If my force is 2 newtons, the block doesn't move. If my force is 10 newtons, the block doesn't move. If my force is 13.734 newtons, my block doesn't move. Once my force is 13.7340000000000 infinity, once it is greater than this, by the slightest amount, the block suddenly breaks free and starts moving to the right. At that point, you are in kinetic friction, and you redo the whole problem. You reset the whole problem as if the block's moving and there's kinetic friction. You stop dealing with static friction right here as soon as it breaks loose. But what we normally say in problems is we'll say a block is just on the verge of sliding. What force is required if mu is 0.7 and the mass is 2? So you do this and you'd say, oh, well, the force required to make it move would be 13.734 newtons. Anything greater than that, and it begins to move. That's usually the type of questions you get with static friction. Sometimes you might be given the force and then you have to find mu. That happens too. But yeah, let's do an inclined plane because I want to show you one potential hang up. So imagine we have real simple problem. We just have on a 30-degree, we have a 3 kilogram mass. And it's not sliding down because there's static friction here. So remember again, we draw this way. This is normal. This is M1G sine of the angle. The weight down is M1G cos theta. And then because it's trying to slide down, right, we have a force of static friction. And I'm going to say that X is positive that way and Y is positive up, but it doesn't matter really, because watch. We know that MAX and MAY are 0. And what we get for MAX, if we chose that way, we would get M1G sine theta minus mu n, because the force of static friction is, of course, mu n. Not minus mu n, it's mu n. It's negative because I chose that way. I could have chose that way. And had I chose X to be that way, I would get that 0 was equal to the force of static friction minus this. But those are the only two forces, and because they're set to 0, in fact, it doesn't matter how many forces we have, because this equals 0, we can move it to the other side of the equation, and nothing changes. So it doesn't matter which direction we choose X to be in. Same with Y. We're saying it's up just to make sure our vectors end up with the appropriate signs, but Y could be positive down, and this would just flip sides, right? Okay, so I know that N is M1G cos theta, and I know that M1G sine theta is equal to mu N. Move this over, move mu N over. So N is that, and so I get M1G sine, I really want to write it like this, is equal to mu. So M1G sine theta over M1G cos theta. These cancel and you get tan theta. And what that says, remarkably, is that the coefficient of static friction only depends on the angle of the incline. That's weird. And that it doesn't matter whether it's sandpaper or kind of slick ice. Yeah, that doesn't seem to make sense, right? So yeah, this isn't the best model for friction. Unfortunately, friction is so complicated, we really can't model it. So we do our best, and our best is mu s and mu k. So once you overcome tangent of the angle times the normal force, this thing moves. So what is mu s? Well, what is tangent of 30? Tangent of 30 is, tangent of 30 is 0.577. So this is about 0.58. And we could figure out things like what's the normal force or what's the force of friction. The force of friction, remember, is mu n. So that's mu times mg cos theta. This is the normal force. So if this was a 3 kilogram block, I would get 0.58 times 3 times 9.81 times cosine of 30. And that would give me 14.78 newtons. Conversely, what is the weight in the x? Well, that's 3 times 9.81 times sine of 30. Remarkably, it's equivalent 14.715. I rounded some stuff. So I think because I rounded mu up, those numbers aren't quite the same, but I get that the weight in the x, which is mg sine theta, is 14.72-ish. They should be exactly the same though, because the thing's not moving. It's got static friction is keeping the block from sliding. And this is only true if it's just about to slide, right? If this were somehow less than what it took to slide, you would have no way of knowing what mu is. Because this force of friction is only the friction required to stop it from sliding. That doesn't tell us what this actually is unless the problem says it's on the verge of sliding. Okay. What if this was actually 1? You would have no way of knowing. You would just know that it was enough to overcome the weight trying to pull it down the incline. Static friction is a pain. So the last thing I want to talk about is this same problem, except I want to do it again as with a force on it, because this is actually super important. Same 30, same 3 kilograms, same mass, although now I'm going to have a force. Okay. And so when I do this, I get N, and I get mg cos theta, and I get mg sine theta, and I obviously get F, the force. But now I have to put my static friction force, and that's the problem. I could put it one of two places. I could either put it here, or I could put it here. Let's pretend we're going to put it here first. Force of static friction. What I get is I get, of course, MAY is 0 is N minus M1 G cos theta. And MAX is, doesn't matter which way I put it, I'm going to say that X is that way. Let's say I'm imagining that I'm pushing with the force, F minus mg sine theta minus mu n. And so what I see here is that I get F is mg sine theta minus mu n, or better, the weight in the X, plus the force of static friction. So the force, if this is not moving, the force applied, and it's just on the verge of starting to move, the force applied has to be equal to the weight and the force of static friction to keep it from sliding. Because in this view, the force I'm applying here is being opposed by the weight in the X, and it's being opposed by the force of static friction. But what if I said, oh no, what it's actually doing is it's trying to slide down. So the net motion is actually trying to go down, and my force of static friction is here. Then what I would get is MAX is 0, is F plus force of static friction minus weight of X. And what I would see is that my weight of X had to be equal to the force plus the force of static friction. Basically, as it tries to slide this way, right, the force of static friction and the force that I'm pushing are stopping it from moving. That's a contradiction. They can't both be right? One of them has to be true. And that's a problem that you run into. In general, this is why I don't put static friction on exams, because you can get cases where you have contradictions and there's no real right answer here. I don't know what the right answer is, to be honest. I don't think anyone does. Essentially, maybe what the right answer would be is you would take the weight in the X minus the force, and whichever one of these wins, the force of friction opposes that one. So whichever one of these is greater, the force of friction opposes that. Maybe. I don't know. Friction's weird. It's super complicated. And so we have to do our best, and our best is this experimental coefficient thing where the force of friction is some coefficient times how hard the object pushes into the surface. Unfortunately, like I said, that's the best we can do right now. You might be an engineer and go to grad school and figure something out for friction. But friction is complicated. It's weird. Okay. All right, moving on. We're now going to start talking about and do a bunch of problems on kinetic friction, which just means that friction when we're sliding. And this is how we're going to 95% of the time use it. Let's say this block is being pulled by a force, right, in this direction, and there's on the surface 0.3 coefficient of kinetic friction. So it's got some velocity. It's moving to the right with some velocity. When I draw the free body diagram, normal, mg, my force, because the velocity is that way, I'm going to say this is x positive and up is y positive. Because the velocity is that way, the force of friction is that way. And so when I write my equations, m1ax and m-ay, I write 0, it still can't move off the surface, mg, and F minus F of friction, which is F minus mu n. From this equation, I see n is mg, so I get that max is F minus mu n. And I want to find the friction or the force if A is 10 meters per second squared and my mass were 2 kilograms. All right. So I'm trying to find F, and F is ma plus mu n, which is mg. If I plug in numbers for that, given the quantities I gave you above, I get 20 plus 0.3 times 2 times 9.81, which is 25.89 or 25.9 newtons. So in order to pull this with an acceleration of 10 meters per second squared, if there's friction, I would have to pull it at 25.9 newtons. If there were no friction, it would be 2 times 10. The force would just be ma, and that would be 20 newtons. So there's 5.9 newtons worth of frictional force in this problem. And we can see that by multiplying 0.3 times 2 times 9.81, and we get 5.886 newtons. So the force, this is the force of friction. Oftentimes on an exam, I'll ask you, what is the force of friction in this problem? What I want you to do is write it, mu n. I'm asking you to identify n, and I'm asking you to solve it for the actual value. This is 2 times 10, and this is 0.3 times 2 times 9.81. So this is 20, and this is the other 5.9. Okay, that's it. That's all you have to do with friction. What gets hard is making sure that you get n correct and making sure that the sign or the vector points in the right direction. So we've effectively now added a 5th force to our checklist: normal, weight, push-pull forces, tensions, and now friction. All right, inclined plane. Again, this is, I don't know what that is, sorry. This is another simple problem, but I want to do something different on this, okay? Imagine this guy's sliding down with constant v. And there's friction. Mu is 0.4. The mass is 5 kilograms, right? And so I want to know if this thing's sliding down, I want to know what angle would give this thing constant velocity. So how do I do that? Well, I draw my free body diagram. Remember, it's on the incline, so this is mg sine theta. This is mg cos theta. This is force of friction. This is down the incline, positive x, and this is y positive. I'm going to write a is that way, even though there's no a, because it's constant velocity. Constant v implies that A is 0. And we already know A and the Y, A perpendicular to the surface is 0. So I write MAX is 0 and MAY is 0. And then I write those forces, N minus mg cos. And this is mg sine minus force of friction. Remember that the force of friction is mu n. Okay, so what I get is I get mg sine theta is mu times n, but n here is mg cos theta. So this is mg sine theta is equal to mu mg cos theta. And again, if I divide through by mg cos, this goes away. I get that mu is tan of theta, or I get that the angle of this must be mu. Tangent of arctan, I should say, of 0.4, I hope is actually a number, is 21.8 degrees. So this angle would be 21.8 degrees. That's the angle that it would slide down at constant velocity. It wouldn't accelerate and it wouldn't decelerate. Basically, at that point, the weight and the force of friction are equal, which is exactly what we're seeing right here. We know that, but we're seeing it mathematically. Going through Newton's laws, we arrived at it mathematically, which is great that that actually worked. This is pretty common to see in these Newtonian equations, that they'll throw that constant velocity wrinkle at you, which means that there's no acceleration. And just be aware, it's kind of like the starting from rest thing, that you have to know that that means 0 constant velocity. You have to know that that means there's no acceleration. We already know that from chapter 2, but for now, I'm going to do these putting it all together ones that I wrote. I'm not going to solve this stuff. I'm going to talk about how you solve it, but I'll let you guys do it. I'm going to show you the equations and tell you how to do it, but I'm not going to put numbers in. I just don't have the time or the energy. So a flat plane, and we have some pulley, and we have some mass 2, right? And then we have some mass 1. And what's happening here is mass 1 is being pulled that way. Mass 2 is accelerating down. So we're moving. We're not starting from rest. We're moving so that we can have kinetic friction. So there's some velocity. It's headed right. It's headed down. So I want to draw my free body diagram for number 1. I know I have a normal force. I'm going to call this normal 1. I know I have a tension, and then there's friction here with some mu. So I have a force of friction in that direction. And I'm going to say that x is positive in that direction and y. And then for this one, this is my hanging mass, right? I'm going to say that y is positive down or x is positive down, whatever you want to call this direction, because this is m2g and this is the tension, right? And that's the only forces on here. The reason why I'm calling this positive is follow the rope, right? I also note that a of 1 of x is equal to a2 in the y, right? They have the same acceleration because massless, stretchless, frictionless ropes. So we can write these equations, m1ax, m1ay. This is 0, n minus m1g, which tells you that n is m1g, n1 I should say. Although I don't need the 1 because this doesn't have a normal force. And this is T minus force of friction, which is T minus mu n, which is T minus mu m1g, right? m2ay is m2g minus T. I can substitute in, solve this for T. Solving it for T, I get m1a, I'm just going to call ax a and ay, this AY, not A1, but A2Y, they'll both be A. This is M1A plus mu M1G. And if I plug that in here, I get M2G minus M1A minus mu M1G. Putting that all together, I get M1 plus M2A is equal to M2G minus mu M1G. I can solve this for mu, move that over, and I'll do that right here really fast for you. I'll do it right here. This will give me M1G is M2G minus M1 plus M2A, or mu is, if I divide both sides by M1G. If I gave you A and I gave you the masses, you could tell me what mu is pretty easily, right? So I went through this really fast, but it should be getting faster for you. If you've been following these examples, it should be getting fast. You should be able to figure this stuff out pretty fast. This is our frictional force. I want you to note this though, again, remember that our net force is the total mass times the net acceleration is the sum of the forces. Well, we only have two forces acting on this system. We have a force pulling it down, which is M2G, and we have a frictional force trying to stop it from moving. So if you imagine this was my big system, the friction is trying to pull it that way, and the weight of 2 is trying to pull it that way. And you can see that, which is really nice that you can see it. It's essentially the two forces, external forces on this, are a weight and a friction. And they're trying to work opposite of each other to influence the acceleration. That's pretty nice that we can actually see that. Yeah, I wrote a bunch of examples here. I don't know how many I want to do, but flat plane with friction and a hanging mass, we just did that. Constant B would be that A would go away, so this side would be 0, and you would get M2G minus mu M1G would be, so we get 0 is M2G minus mu M1G. And what we'd see is that mu M1G is M2G, or mu is simply M2 over M1, G to cancel. So in this case, if it was moving with constant velocity, you could find mu from this equation. You would do all this stuff the same, but you would set this equation to 0 because A is 0. We could also ask for the tension, and you just plug it in there, or you could plug the tension in here if you knew A. That's not too hard. This problem is a bit harder. This is actually the hardest problem I want to show you so far. We have two different incline planes. One is at, let me actually grab my notes on it. I definitely don't want to do all of this stuff. I don't know where my note is. This underneath me. One is at 30 degrees. One is at 40 degrees. This mass 1, is, let's say 4 kilograms. 4 kilograms. Mass 2, I'm going to say is 15 kilograms. They're connected over a pulley at the center. Okay. This side has mu of 0.5. This side has mu of 0.4. And while you can see, you can guess pretty much. And the reason why I did this was to make it totally obvious. But if this thing were released from rest and we didn't consider static friction at all, it could overcome static friction. We know that it would slide. We know that it will slide in the to the right. So the reason why we know it will slide is because 15 kilograms is so much bigger than 4 kilograms, right? And what we're really worried about is that this won't be enough to overcome the friction here. If these were close, if these were both, say, 4 kilograms, there might be no way to figure out which way this thing's going to slide. And what you'd have to do in that case is you'd have to guess, and you might be wrong, and then you'd have to backtrack and fix it all. I won't do that to you on an exam, but you could run into this problem in other cases, right? So I'm going to tell you that this thing's going to go this way and this way. So when we do number 1, and for both of these, we're going to consider y to be up positive and x to be that way positive. So N1 is M1G cos theta 1, where theta 1 is 30. It's going to have a tension. This is number 1. It's going to have a force of friction, which is mu1 or mu N1. And it's going to have a weight M1G sine theta down the down that incline, right? But it's trying to travel that way. We're going to assume at the beginning of this problem it is traveling that way. The free body diagram for number 2 is N2 M2G cos theta 2. It's headed down M2G sine theta 2, and tension and force of friction number 2, which is mu N2. This is mu 2 N2, right? And so what we see in this problem is the friction, because it's sliding downward, the friction is up the plane for mass 2, it's down the plane for mass 1. And when we do this, we just write our M1 A1X, M1 A1Y. Again, this is 0, so N1 is, N1 minus M1G cos theta 1. Same thing here, M2 A2Y is 0, is N2 minus M2G cos theta 2. This, because we're choosing that to be positive, is T minus M1G sine theta 1 minus mu N1. M2A2 in the X is M2G sine theta 2 minus T minus mu N2, where N2 is that, N1 is that. Once you do all this, you would substitute this T into there. You're going to get this ugly equation. So you're going to substitute for M1, M1G cos theta 1, and for N2, M2G cos theta 2. Plug that in for N2. This is the right side's mu, 0.4. This is the left side's mu, 0.5. Plugging those things in, the masses are different. You're going to get something that says M1 plus M2, noting that A1 of X is A1 of X is equal to A2 of X, and we're just going to call it A. That's got to be equal to, solve this for T, plug it in there. That has to be equal to M2G sine theta 2 minus mu 2 M2G cos theta 2 minus M1G sine theta 1 minus M1G mu 1 cos theta 1. All of these. How do I know that? How can I write that down? Well, I know that the force in the positive direction is the weight along the incline of 2. The force of friction on 2 is opposing it. That's what this is. It's mu2 times m2. It's also being pulled back by the weight of 1, which is m1g sine theta 1, and it's being pulled back by the friction due to that. So you have these. What I really want to talk about here, though, is imagine I mess up and I give you this problem and you end up with some negative number, meaning that the force of friction is greater than the weight here. I mean, I guess the weight of one could be greater, but in general, it would be that the friction force can't be greater than the acceleration, well, than the net force. You can't get a negative force from friction. The reason why you can't is this thing, friction can't cause this thing to move in the direction of the friction. So if that ever happens, you've done something horribly wrong. You've got a problem. So imagine this. I'll do a different example that's easier, that I don't have to do a ton of algebra for. New slide. So imagine this. Okay, I have a force of friction, and I'm pulling with some force, and again, and weight. So MAY is 0, is N minus W, but W is mg, so N is mg, because this is mg. MAX is, I'm going to say that X is going this way, is F minus F friction, which is F minus mu N. So MAX is F minus mu mg. Now let's say that this is 0.3 and this is 10 and this is 9.81 and this is 3 newtons. So 0.3 times essentially 100, this is going to be bigger than this. And so what I end up with is MAX is something like minus 27 newtons. Well, that's telling you that this block is being accelerated to the left. That can't happen due to friction. Friction can't make a object move. It can only stop motion. That's really important that you understand, okay? Just make sure you understand it. Last thing in this section, before we move on to the other topics that are easy and pretty quick, 2 inclined planes with friction and a hanging mass. I just want to show you this. I'm going to draw the free body diagrams for you and then move on. This is a really good kind of test problem. Same problem that we just did. Mass 1 and mass 2, different angles, angle 1 and angle 2. They're connected by ropes to a third mass, right? And this thing's going to drop. This guy's going to head up. This guy's going to head up. So how do we draw the free body diagrams for? 1, I'm going to draw 3 in the middle, and 2. 3 is easy. I'm assuming it has a tension from the left block and a tension from the right. I could also write this as 1 and 2. It might make more sense to be 1 and 2. And then it has a weight, which is M3G, and A is down, therefore positive down. Now, number 1 has M1G sine theta 1, and it's going to have a force of friction, mu N1. It's going to have N1. It's going to have M1G cos theta 1, and then it's going to have tension left. This one is going to have tension right, and 2 M2G cos theta 2, and mu N2, and M2G sine theta 2. And then you would just write this guy. The only equation you would have, because it's down positive, would be N3G minus T left minus T right. This one, and this one for that matter, they'd kind of be the same with a little bit of difference. M2AY would be 0, and that would be N2 minus M2G cos theta 2. So you know that N2 is M2G cos theta 2. And then M2AX would be that way. We're going to assume that this is X positive that way. Why? Because it's moving up the incline. So M2AX is T right minus mu N2 minus M2G sine theta 2. Similarly, this guy, I'm going to assume X is positive that way. And I would get M1 A1X is T left minus mu N1 minus M1G sine theta 1, and M1 A1Y is 0 is N1 minus M1G cos theta 1. Now, solve this for TL, and what do you get? You get TL is M1 A1X plus mu N1 plus M1G sine theta 1. Now, I need to note that however this guy moves, because these are stretchless massless ropes, we assume that these two move with the same acceleration. Therefore, A1 of X is equal to A2 of X is equal to A3 of X. So this A is A, this A is A, and this A is A. Once you have that, solve this one for TR just like you solved this one from TL, plug them in here, and solve this for A, and you're done. That is a ton of algebra that is awful. And not actually all that hard, easy to make a mistake. But the important thing is knowing things like the direction of the forces, making sure your friction is in the right direction. I check for signs, sign errors. What this should end up being is M1 plus M2 plus M3 times A, and then the sum of all the forces. Well, the force on this one is the weight in the X of 1, and the weight in the X, I'm sorry, it's wrong, is the weight of 3 in the Y direction, I guess. So this would be the weight of 3 down, M3G, minus the weight of 1 in the X minus the weight of 2 in the X. That's trying to stop this thing from falling. The weight in this direction is trying to stop the thing from falling. Minus the friction of 1 minus the force of friction of 2. The friction is also trying to stop this from falling. That's what your final equation will look like. It'll have these terms. This is mu 1 N1 is your force of friction 1. Mu N2 is your force of friction 2, right? And so it'll end up looking something like this. In fact, it'll look exactly like this when you do the algebra all right. And so I can kind of spot check your algebra and what you did, but I'm going to look for the signs. I can read this as the total force on the system, total mass times A, is the weight down minus the weight, minus the weight, minus the friction, minus the friction. You can read that. That's kind of the difference between what you do in a math class and what you do in a physics class. Is this definitely has an English, you could in a way explain what each of those quantities is to a person without using math. You could say the net force on this is equal to the weight of 3 minus the weight of 1 and 2 along the incline minus the forces of friction, right? You can state it in words without using math. You wouldn't be able to get numbers, but you could. So in general, once you do this, you would find A. One really nice thing to do in this type of problem is to say that A is 0. It saves a little bit of time because all these MA terms go away, and this side is 0, and then you can find, for instance, maybe what the mass of 3 is, because this is M3G. So you can move everything else over to the left side of the equation and solve it for M3. Stuff like that is usually what I do in these problems, if I do a problem like this. And yeah, I will do problems like this. If not on the exam one, on the final, you might end up with a problem that looks like this. All right, so that's it for those types of problems. You've seen almost every type. The problem is that you can get creative and just keep adding blocks and pulleys and redirecting forces and having friction. And there's a million different examples of block and pulley Newtonian problems. They're useful because they are a general representation of, or a really simplified model of all sorts of phenomena in nature and biology, computers, chem, engineering. We might be talking about blocks on an incline, but we really mean a fish trying to get its way against, a current, or, we mean, I don't know, stresses between materials in an engineering project. We mean cells dividing in, or pulling each other around, or a virus invading a cell in biology. We can use it to model almost anything, because everything can be represented as a point particle at its center of mass, and then you just figure out what the forces are acting on it to get the acceleration and to figure out what the motion is. It may seem really simple, but if you go to grad school, that's what you're going to be doing, is making models like that. Grad school in the sciences is making models, except they're refined to understand things like what friction actually is, and to get a better number than some number times the normal force. But you will find that a lot of models are simple enough because they give you a pretty good answer, a close enough, a good enough answer for human experience. And that's pretty cool. So one of the things that we did earlier was we talked about free fall. And we said, oh, no air resistance. Well, we're actually going to talk about air resistance. And in fact, any fluid, when we get to fluids after exam 2, we'll see some of this again. But for now, let's imagine air. And so we know that if something falls long enough, it eventually reaches what's called terminal velocity, because the air resistance builds up. And we're going to look at what that is. How do we model drag? Well, it turns out that experimentally, we just come up with a formula, throw a constant on it, and figure out what that constant is. So we know that the drag force, this is a force, and you could write this F of D, or you could write it D. Your book writes it D. I'm going to write it D. That this thing depends on a couple things. We're going to assume it's approximated by a few things. The number one most important is V squared, the velocity squared of whatever's falling. The faster it goes, the greater the drag force. And in fact, it's exponential, or a power, to the power of 2, okay? It's also got to depend on the density of the air. If you fell in a vacuum, so the density of, I'm going to put air, but it really would be fluid. If you were falling through water, you would still have a drag force on you. I'm going to put air there though. So the more dense the air, the greater the drag on you. There's more stuff hitting you, slowing you down, because that's what it is. The air molecules are slowing you down as you collide with them. So it makes sense that this better depend on the density of the air. It's also going to depend on how much of you is in the wind. Imagine you have a big fan, right, blowing air at you. If you're facing it full on, right, it's blowing against your body really hard. You turn sideways and it's only affecting you a little bit. So what we call that is a cross-sectional area, and I need to talk about that. If I look at a cylinder, right, if I'm pushing a cylinder towards you, I see this whole face, and it actually looks like a rectangle, right? If it's going that way into the air, right, what I see is I see the top of it. And so I see a disk with an area of pi r squared. If I had a cube coming at me, I would see a square, right? If I have a sphere coming at me, what I actually see is a disk, because the cross-sectional area of a sphere If you cut a slice out of a sphere, it would look like a disk. This depends on the cross-sectional area. I write that as a cross. Sometimes you're given it, sometimes you have to know what it is. In an exam problem, you'll be given or told what it is. But in real life, you could figure it out. And we're going to talk about how it affects everything really soon. In fact, it affects everything by the square of it, okay? So if we do that, the last thing that we need to do is we're going to throw a constant on there. And that constant is the drag coefficient of whatever you have. So if a sphere were made of rubber, let's say, it might have a different drag coefficient because the rubber surface is a little bit more rough than, say, an ice sphere made of ice or a raindrop. Water would have a different drag coefficient than, you know, a piece of leather or something. So what we say is the drag force is C V squared, the density of air, the cross-sectional area of the object divided by 2. I feel like something's missing. Let me make sure that I didn't inadvertently drop anything. As your book gives it. Nope, it's all there. And so coefficients are either found because you know everything else, or they're looked up in a table. Your book has some terminal air speeds, so you could figure out if you knew cross-sectional area, maybe you could figure things out. We're going to talk about a really, the one example that you almost always think of, and that is a skydiver. Okay, if you've never seen a video of a skydiver, you've never skydived, what skydivers will do is they'll put their arms back and they'll basically face downward into the wind to travel faster. And if they want to travel slower, they put their body out like this as the wind hits them. What they're doing is they're increasing their cross-sectional area to slow them down, and we're going to look at that, okay? So before we do, we're going to talk about terminal velocity, and then we're going to come back. If you're falling in free fall, you know that you have a weight, right? Which is mg. And you have this drag force that acts in the opposite. We're going to say that A is down. We don't know what A is. It's not G. And we have this drag force that's acting upward. We're going to assume that Y is positive down. Okay, so what we write is we write MA is equal to, and because we're saying positive is down, weight minus drag, okay? And therefore MA is equal to mg minus this drag force, and remember this drag force is v squared A, okay? Now, eventually, you'll hit the point because as you fall, your B is increasing, which means your drag force is increasing because your velocity increases the longer you fall. Eventually, you'll reach the point where these two things are equal and your acceleration becomes 0. So the longer you fall, the less your acceleration until you reach a terminal velocity. This is mg c rho v squared A cross over 2. If I set these equal, I get mg is c rho v squared A over 2. I can solve this for v. V squared is mg times 2 over c, density of air times the cross-sectional area. Taking the square root here, right? This is terminal velocity. Terminal velocity is therefore 2 times your mass times gravity divided by your coefficient of drag, the density of air, and your cross-sectional area. So let's go back and look at this. When you're like this, your cross-sectional area is 0.78 meters squared, let's say. And when you're like this, it's 4 meters squared. So A cross, you make yourself much bigger and give yourself a much bigger cross-sectional area. We're going to find out what V is in these two cases. And we got 2 mg over C rho cross-sectional area. Did I leave anything off? Nope. Let's say you're a 60 kilogram person. That's like 130 pounds. I gave you the cross-sectional areas. Your coefficient of drag, usually they're like between 0.4 and 0.7 or 1.0. Let's say it's 0.6. Okay. The last thing we need is the density of the air, which we talked about in the math review, 1.2 kilogram meters cubed. That is the density of air. So what will V be? Well, V will be 2 times 60 times 9.81. Your drag coefficient is 0.6. Your density of air is 1.2, and your cross-sectional area is 0.78, right? So how fast will you fall? Well, 2 times 60 times 9.81 divided by 0.6 times 1.2 times 0.78 is 2,096. If I take the square root, 45.8 meters per second. Okay, this is if A is 0.78 meters squared. So you head into the wind and streamline yourself and you kick up to almost 100 miles an hour. Now you want to slow down. So you've fallen out of the plane and you want to slow your ascent. So you go to this arms wide and huge cross-sectional area. And what you get is V is 260, 9.81 over 0.6, 1.2, and now 4. When I do this, 2 times 60 times 9.81 divided by 0.6 times 1.2 times 4, I get 408. The square root of this is 20.2 meters per second. That terminal velocity, you might survive. That's hitting the ground at, 45 miles an hour. I'm not saying you will, but people have. If you ever fall out of a plane, make your cross-sectional area into the wind as big as possible to slow yourself down. That's kind of what a parachute does. Is a parachute creates this huge cross-sectional area to the wind and captures the wind, slowing you down immensely. That's what drag force is. You don't need to know this for the exam. In fact, you don't need to know this ever again for this class. We're going to talk about drag at the very end in a different way, something called damped oscillations, but we're going to do it differently. So drag force is cool. It's fun to do. It's cool that you can see the realistic results of things, but it's not particularly useful. It's also experimental. That coefficient of drag tells you that basically they tested a bunch of objects by dropping them and seeing how their terminal velocity changed. And so they figured out the drag coefficient. It's important in engineering, especially for like automotive engineering, where you're trying to make cars that either do or don't have drag. Sometimes you want drag, sometimes you don't. It's super important for you guys as far as how you would model a process. So this whole idea of taking a force and saying, well, it depends on V squared, and it must depend on the density of the air, and it must depend on the cross-sectional area, and it must depend on some coefficient. Well, there's ways in stats to figure out whether or not any of those variables are actually related, are actually important in your model. And these were important in the model of drag. So they aren't ad hoc. They didn't just say, oh, well, maybe velocity, let's throw density of air in there. There's statistical analysis that you can do to show that it does depend on the velocity squared and not the velocity cubed or something else. We should note here, since we're here, meters squared over seconds squared. Density of air is kilograms over meters cubed. Cross-sectional area is meters squared. Out of this, we need to get newtons, which are kilograms meters per second squared. We see that this is kilograms meters per second squared. This is m to the fourth over m to the third, which is m over squared. So the coefficient has no units. It's all here. And these unit-wise do match your drag force. They are a force, they're newtons. So that tells you that this model is probably at least physically right. It gives you the right units. So how well it models real drag, I don't know. Air and fluids. Fluids are one of the hardest areas to do right. They offer a lot of money if you can solve a couple of outstanding theoretical ideas in fluids. Fluids are too complicated for us, or at least they used to be, back when we didn't have supercomputers. Computers are getting fast enough that they can model fluid flow, and probably in your lifetime, they'll be able to. When I did biophysics, it was pretty good. They could model it pretty good, but we always had problems with the model not quite converging. And that's a computer term or a math term that's just, it sucks when you wait 4 hours for a computer to figure something out and it doesn't get a good answer. But yeah, that's something for you for down the road. Okay. Now, the last three things we're going to talk about are actually going back into uniform circular motion. I'm saying this is with forces because last time we said, oh, this object's going around. We didn't really state it, but we were talking about horizontally traveling. The reason why is everywhere there, it would have a force due to gravity, a weight, and we didn't want to consider it. Now what we're going to do is we're going to do horizontal and circular motion with forces. So if this is horizontal, right, imagine that you're on a Ferris wheel. If you don't know what a Ferris wheel is, it's like a seat that's attached to a big ring, and they, at like a carnival or a fair or Disneyland or wherever, you'll be able to ride it, and you go up to the top and you come back down to the bottom. And as you're sitting on the seat, there's a normal force acting up on you. The seat's actually pushing on you. You're pushing on the seat, but we don't care about that. We only care about you. So in this motion, as we do this, we're going to look at the top of the motion, the bottom, the left, and the right. We can draw a free body diagram. And for the left and right, they're almost the same. You have a normal force up and you have your weight down. And then because you're moving in uniform circular motion, you have this ARAD. We're assuming that you're moving with constant V around this circle. Therefore, to the center of this circle, you have, and I just made a huge mistake, don't ever draw ARAD as an actual vector. It takes the place of your acceleration vector. So we have ARAD pointing to the center. We have no acceleration up or down because you're sitting on your seat, right? And so when we look at this, if we draw U, and I should say that this is the R direction. So when we draw this, we say MAY is equal to, sorry, I was realizing that I may need to fix some, no, I'm fine. MARAD is equal to N minus W is 0. And MAX, which is MARAD, remember, we're only on the left and right. On the right, it would be N, weight, and ARAD would go that way, is equal to 0. There's nothing pulling you in, right? Okay, so, and again, I gotta stop drawing it like that. That's not a vector that's attached to the actual mass. So that part's not so interesting. What is interesting is at the top and the bottom of the motion. And it's something you can test at home. So let's draw at the top and at the bottom. So at the top, you still have your normal force, right? And you have your weight still. But now, because you're going around this circle, you have an A-rad acceleration vector that points down to the center of the circle. And at the bottom, you have your normal force is up and your weight is down. And you have an A-rad vector that points upward. So at the top, MA-rad is N minus, I'm sorry, weight. And if I get these wrong, you'll know. And at the bottom, MA-rad is N minus W. Other thing, remember that A-rad is V squared over R. Don't forget that. But so here, if you're in your car, you actually feel this in your car. If you've ever gone on a road that dips down and comes up on a hill, at the bottom here, you feel yourself pushed down into your seat. And at the top, you feel weightless. The reason why is your weight, right, is MA-rad plus the normal force when you're at the top. Sorry, I did that wrong. The normal force acting on you is your weight minus MA-rad at the top. The normal force at the bottom is MA-rad plus your weight. So the faster you're going, the higher, as you go over this, the faster, this is mv squared over r, the faster you're going, the less normal force on you. You feel like you're floating away. When you're at the bottom, the faster you go, the more you push, the normal force pushes on you, and you feel like you're sinking into the ground or into your seat. When you go through bumps, that's why. This is exactly why. It's the normal force that you're feeling. It's actually your reaction to the normal force you're feeling, but we'll talk about that later. Next time we bring up uniform circular motion. There's this other idea, and it's a problem given in the book, of a guy riding a motorcycle inside a loop. So he's going around and around and around. Here, though, the normal force is always going to be down for him because it's always off. So at the top and at the bottom, the top, the normal force is pushing on him. And at the bottom, the normal force is pushing up. At the top, A-rad is towards the center of the circle, and his weight is down. At the bottom, his weight is down, and A-rad is up. And again, MA-rad is now N plus W at the top, and at the bottom, MA-rad is N minus that. Keeping in mind that this is MV squared over R is N plus W. In the book, it talks about this, but basically, in order for him to stay on there, he has to be going no faster. Well, at his maximum speed, the normal force is 0. Otherwise, he would have a normal force. So at his maximum speed, when V is a max, N is equal to 0. So this goes away, and weight is mg, and we see that mv squared over r is mg. Cancel the m's, and you get that V is equal to square root of g times r. That's the fastest he can go. If he goes slow, or I'm sorry, that's the minimum he can go. If he goes slower than that, he will actually fall. Or faster than that. Yeah, I don't remember. Making a butchering this, which is okay. Just know that you can find mv squared over r is equal to n minus his weight on the bottom. So mv squared over r is equal to n minus mg, or m v squared over r plus g is the normal force at the bottom. At the top, it's mv squared over r minus g is equal to the normal force. And so if for some reason the normal force became negative, he would fall off. Okay, and so we need, when this is 0, you can see that this goes away and v is g over r when it's at a maximum. He needs to, is it a maximum or a minimum? That's what is bugging me. It's problem 6.04. Yeah, it's the minimum value. If he doesn't go that fast, if he allows v to be less than that, then square root of g over r, he will actually fall. And you got to kind of read through it. It always confused me, to be honest. But yeah, you can do some stuff with uniform circular motion. The next two things that we do with uniform circular motion are much clearer. And that is when you're driving or riding a bike and you're taking a turn. Okay, so you're taking this turn. We'll pretend you're in your car, right? So your car looks like this. And as it takes the turn, what makes your car turn? It's actually the friction on the wheels that makes it turn. And that friction is still mu n. Okay, so we know that when you're rotating, you have a rad. Let's say you're in uniform circular motion. We know that you still have a normal force up and a weight down, which is still mg. And so what we see here is that in that y direction, may, still 0, you're not flying off the road. The normal force is mg. And in the ma rad direction, the only force, I should draw like this, is the force of friction and weight. There's no acceleration this way. There's an a rad acceleration to the center of the turn. Ma rad is mv squared over r, right, is mu, and n is mg. Cancel those, and we see that v is mu gr, okay? What that means is this is the fastest you could go without sliding, because this is the force of friction, and if this force were greater, you would fly off the turn. So the posted speed, let's say the road is 0.7. Mu, it's got some gravel, and you're on a 100-meter radius, right? Big old turn. The fastest speed you could take without sliding off the road, without overcoming the friction, your tires overcoming the friction and you're sliding out of the turn, is square root of 0.7 times 9.81 times 100, 26.2 meters per second. That is around 55, 60 miles an hour, and you're good. If you go any faster than that, your wheels start sliding. They overcome the friction and you fly off the turn. This is super important in real life because what happens when it rains? So we just found that V was mu gr. That same turn when it rains, if it's flat, mu might drop, or it snows, to 0.05, let's say. Well, let's not go that low. Let's go to 0.15. If mu dropped to 0.15 and this still had a 100-meter radius, what's the safe speed? Well, 1.5 times 9.81 times 100 is 1.5 times 100 times 9.81. Take the square root of this answer. I get 38. Okay, 38.36 meters per second. What did I find before? 26? I must have done something wrong up here. 0.7 times 9.81 times 100. No, I did something wrong. Oh, I see what I did wrong. I'm so sorry, you guys. This is not 38.6. This is 0.15. 0.15 times 9.81 times 100 is 147. Take the square root of that, I get 12. So this is 12.13 meters per second. Okay, so that's the maximum on a rainy, wet road that has no traction, no friction. You have to slow down to about 25, 30 miles an hour to take it safely without sliding off the road. If you look and see, whenever you're driving, you might have noticed, especially on like the freeway, it'll tell you how fast you can take an off ramp. It'll say like 25 mile per hour max on this turn. Where they're getting that from is, we're going to see when we do banked where it actually comes from, but where they're getting that from is, if the conditions were really, really bad, what would be the safest you could take the turn at? But remember this, particularly in California, you all know it, people drive like crazy in the rain. The rain can reduce the coefficient of friction on the road by to a quarter of what it normally is, which means you'll start sliding at a much lower speed. Slow down in the rain. Even worse if you hit like black ice, if the road freezes. That doesn't happen too much here, but it happens in places where it snows. You'll slide right off the road because you have no friction at your wheels to push you around the turn. However, we can save you, and this is what's super cool. We can save people because imagine instead we have a bank. We have a bank turn that you're on. And in fact, there's no friction on this bank turn. So just like we did before, we have theta, we have a normal force acting on you, and we have a weight down. And there's an acceleration a rad. You might be tempted to do this. Let's flip this and do it along the incline. We don't want to. What we really want to do is we want to divide n up into nx or ny and nx. This will be our weight. Now, if I know that this is theta, this is phi, this is theta, and this is a right turn, so this is phi. What that means is this is actually, if I take this and this is phi, then this is n sine phi. But phi and cosine, or phi and theta, are a pair. They're 90 degrees off. So sine of phi is actually cos of theta. So I get that this part, this ny, is n cos theta, and the nx is n sine theta. When I draw my free body diagram, I get n, what did I say, sine? N cos and n sine. I get n cos theta. I get weight, which is mg. And then I get n sine theta, which is the normal force, is actually pushing me into the turn based on the banking. And I have a rad going that way. So in the y direction, I have 0 is n cos theta minus mg. Therefore, n is mg over cos theta. In the x direction, assuming to the right is positive x, I have ma rad is equal to n sine theta. Okay. Now n is this mg. Remember that this is v squared over r. N is mg over cos, sine over cos. And what I get here is I get mv squared over r is equal to mg tangent theta. The m's cancel, and I get that v is g r tan theta. That means that the fastest I can go doesn't depend on the road at all. It depends on the radius, and it depends on the angle of the banking. So if I still have this 100 meter banking, or 100 meter radius on my turn. But if I bank it at 20 degrees, how fast can I go? If I bank it at 50 degrees, how fast can I go? Now, square root, so V is square root of GR tan theta, and I want to do 20 and I want to do 50, and I want to do 85. So if R is 100, what are these V's? Square root of 9.81 times 100 times tan of 20. I get 18.9. So for V, where the angle's 20 for V when it's 50 and for V when it's 85, I get 18.9 meters per second. I can take that turn at almost 40 miles an hour if it's banked 20 degrees without even having friction. And I will go around that turn just because of the banking. If it were 50 degrees, I could do 9.81 times 100 times tan of 50. I can do 34.2 meters per second, which is 72 or 3 miles per hour. And finally, if it was banked almost 90 degrees, tan of 85, I could do 106 meters per second, which is over 200 miles an hour without my tires needing to deal with friction. I could have super ball tires. So the idea here is that if they bank it, they can save you from flying off the road by banking the turn subtly. Even people with bad tires don't need the friction of the road, they just need the banking to make the turn. So if you make a 20-degree banking, even with snow and bad tires, you can still make that turn as long as you're not doing more than 40 miles per hour. That's pretty awesome, and that's meant to save your life. So that's all I got. I'll talk to you guys later. Hope you enjoyed this lecture, and we'll talk more tomorrow. Bye.